When working with hyperbolas, we think we noticed a reflection property for the hyperbola that is similar to the reflection property for the ellipse and the parabola. What we think we noticed is that a ray coming from one focus of a hyperbola and reflecting off of the hyperbola is reflected away from the other focus. Right, for this hyperbola, what this is saying is that this ray coming from one focus, if it reflects off of the hyperbola, it appears, or it is reflected in a direction that it is coming away from this second focus. Or alternatively, if we emit a ray from the second focus, it is reflected so that it appears to be coming from the first focus. So let's see if we can actually prove this. It looks plausible, but that's not a proof. So the first thing we're going to do is, let's label all of these points, I guess, give them all names. So let's call this one F1 for focus number 1, this one for F2, and let's call this point P for just some point on the hyperbola. So notice that we, so just to set things up, let's do two things. First, let's subtract the length F2 to P from the line segment F1 to P. Okay, we get a point, let's call it A. So what I mean is we're going to take this length from F2 to P and cut off an equal distance from the segment from F1 to P. So that gives us this point A right here. Okay. Now remember that this difference of distances, right, this difference of the distances from P to the two foci produces the characteristic length for a hyperbola. So this means that the length from F1 to A is now equal to that characteristic length for a hyperbola that we called 2A. All right. Next thing we're going to do is, at the point P, we're going to construct a line that bisects the angle from A to P to F2. So bisect this angle with a line, and we're going to call this line L for lack of a better name. So we're going to cut this angle right here in half. So that's about like this. That's not quite good enough. Let's see if I can do better. That's a little bit better. Okay, so since we cut this angle in half, this angle here is going to equal that angle there, right? Because after all, we cut the big angle in half. Now, it is going to be, and this is the line L right here. Now it's going to be enough to show that the line L is tangent to the hyperbola. So let me show you why that's enough to prove the reflection property. So if L is tangent, then so let me extend the line from F2 to P. So if we extend both of the lines coming from the foci through the point P, so if L is tangent, then, right, we already know that this red angle equals this red angle, but if L is tangent, then that means that these other two red angles are vertical to the first two red angles. So all of these red angles are equal to each other, but these red angles, these first two are the incoming and outgoing angles for the ray coming from F1, and the second two, these two here, are the incoming and outgoing angles for the ray coming from F1 and then reflecting off the hyperbola. So no matter which ray counts as the outgoing ray, there's a pair of angles that the incoming angle and outgoing angle are equal to each other. Right? The first two, these bottom two angles are equal to each other because of how we created them by bisecting a big angle, and then the angles across are equal because they're vertical angles across the point P. And so all four of these red angles are equal to each other, and so we're done. So if L really is tangent, then we're done. So all we have to show is that this line L actually is tangent to the hyperbola. To show that it's tangent to the hyperbola, we're just going to show that no other point on the line is on the hyperbola. So let's let I be some other point on the line L. Okay, so we've got some other point I on the line L. So what we can do is construct a line from I to F1 and from I to F2 like this. And what we're going to do is think about the difference of these two, because we need to compare that to 2a. Because if it's equal to 2a, then I is on the hyperbola, and if it's not equal to 2a, then I is not on the hyperbola. So to compare, what we're going to do is also add a line segment from I to A, like this. With this setup, we need to notice that some of the different lengths in this picture are actually all the same. So the length from A to P is equal to the length from F2 to P. Okay, and this is just because of how we created the point A. Second thing to notice is that the angle from I to P to A, so this angle right here that I'm marking in blue, is equal to the angle from I to P to F2. Okay, and this is the case because both of these are just a half turn, this blue half turn, minus this other angle at P, which we've already noticed that these two angles are equal to each other, because we created those two angles by bisecting APF2, right? So IPA is equal to IPF2 because of how we bisected APF2. All right. Last thing to notice is that the length from I to P is equal to the length from I to P. That's obvious because that's the same length. But if you look at these three pieces, right, now we have AP equal to F2, we have this angle equal to that angle, and we have IP equal to IP. This means that the triangle from I to P to A is congruent to the triangle from I to P to F2. And this is because this is a side-side angle situation, right? A side angle side situation. If you have two triangles with a equal side angle and other side with the angle in between the two sides, those are the same triangle, right? So in this case, they happen to be mirror images of each other. So these two triangles are congruent to each other, but in particular, right, that means that all their corresponding sides have the same length. So in particular, that means the side length from I to A is equal to the side length from I to F2. Okay, so now these two blue lengths are actually equal to each other. Oops, I didn't want that to... There we go. Okay, so these two blue lengths are equal to each other. The last ingredient that we need is just to notice that there's a triangle right here, this big wide triangle. So in the triangle from F1 to I to A, we can write down the triangle inequality. Remember, the triangle inequality says that the sum of any two sides of a triangle must be larger than the third side, because otherwise the sides just don't fit together into a triangle. So so for this triangle, this means that from F1 to I has to be less than the distance from I to A plus the distance from A to F1. All right. Well, remember that we just noticed that the distance from I to A is equal to the distance from I to F2. So in this triangle inequality, we can replace this second piece with the length from I to F2. Okay. And now what I'm going to do is move this length of I to F2, just move it to the other side. So we get F1 to I minus the length from I to F2 is less than the distance from A to F. So, sorry, F1. Okay. And believe it or not, we're now done, because the distance from A to F, A to F1, if we look up here, that's that characteristic distance for our hyperbola. So the right-hand side of this inequality is 2A. And then what about the difference of the distance from I to F1 and I to F2? Well, this is the difference of the distances from I to each focus, right? If I were on the hyperbola, this difference would be equal to 2A, but it's not. So because of this inequality, the point I is not on the hyperbola. And that means that this line L is tangent to the hyperbola at P. Right? So what we've achieved is we've proved that this line is tangent at P, and as we noted before, that means that all of these ingoing angles and outgoing angles for all of these reflections, these are all equal to each other, and that proves the reflection property for the hyperbola.